Hello and welcome back to Introduction to General Relativity. In the previous lecture, we left off discussing linearized gravity, that is solutions to Einstein's field equations, where we consider the perturbations in the geometry to only to linear order in the perturbation around a flat space-time solution. Well, that's the objective. In this lecture, and in that previous lecture, we ended off discussing diffeomorphisms and isometries, and the reason we were looking at this topic was because we wanted to understand the gauge freedom of Einstein's general theory of relativity and how we can use it to simplify the linearized equations of motion that arise from linearizing Einstein's field equations. So in today's lecture, we're going to continue our discussion of diffeomorphisms and isometries, and in particular look at infinitesimal diffeomorphisms and isometries and show how they can be exploited to simplify the linearized Einstein's field equations. Before that, we just have to spend a little bit more time discussing diffeomorphisms and the gauge structure of general relativity before we look at infinitesimal diffeomorphisms. So if we have a diffeomorphism phi between two manifolds M and N, then, as I emphasized in a very early lecture in this course, the manifolds M and N have identical manifold structure. Okay, that's just in other words, diffeomorphisms are the morphisms in the category of smooth manifolds. And this means that the topologies you get induced on the manifolds M and M are equivalent, and also the smoothness structures and so on. Now, you have to observe that general relativity describes nature in terms of a manifold, right? In terms of a manifold M, and there's some additional data. It's not just that you have a manifold structure that encodes all of space time. You have some additional tensor fields in general relativity. A list of tensor fields. I've written T superscript with J in brackets to indicate there's more than one such tensor field. And the point is that in general relativity, we don't just have the manifold structure. Of course, we have a couple of tensor fields that are highly relevant for Einstein's field equations, the Ricci tensor, the Ricci scalar, the Einstein tensor, and we also have the stress energy tensor. These tensors all play a key role in the description of nature. So since general relativity describes nature in terms of a manifold and some tensor fields, let's write them Tj is just a list of tensor fields, then if some manifold and the requisite list of appropriate tensors fields and another manifold, say N, with a pulled back as appropriate list of tensor fields, have physical identical properties. There's no if there. I'll rewrite that. So here we are getting into the gauge structure of general relativity. So if we have a manifold with some tensor fields on it, Tj, then and a diffeomorphism phi, then the argument is that M and its list of tensor fields Tj and N, the image of the diffeomorphism, and the appropriately pushed forward tensor fields phi star Tj have physically identical properties. And the reason is because all operational quantities in general relativity are built, operational means you can design an experiment to measure them, are built from these tensor fields Tj in a coordinate-free manner. And what does that mean? Well, that means that Jacobian factors cancel. Under contraction tensor operations or tensor transformations. So in this way, like, it's a very simple argument ultimately. Diffeomorphisms comprise the gauge freedom of general relativity. Now that's a fairly general argument, but it doesn't actually help us in the discussion we have now of the linearized Einstein field equations. And the reason is that we want a slightly more specific form of diffeomorphism that we want to focus on, namely infinitesimally small or near identity diffeomorphisms, and those are the ones that we'll use to simplify the linearized Einstein field equations. To talk about infinitesimal diffeomorphisms, leads us to the topic of the Lie derivative and killing vector fields. So we're going to now introduce some additional mathematical infrastructure and in order to describe quantitatively infinitesimally small diffeomorphisms. Okay, we start as before with a manifold M, and now we suppose we have a not one diffeomorphism, but a one parameter group of diffeomorphisms. And we can note that such a flow phi is generated by a vector field V. Okay, that's something that I discussed previously in earlier lectures. But now we've got a general group of diffeomorphisms. We are perfectly able to apply the action of this group of diffeomorphisms to tensor fields. So we can use phi star t, all right, this is the map induced on tensor fields, to define, well, so what? We could define a flow on tensor fields, but we can also use phi star of t to define a derivative type operator. Different or distinct from the covariant derivative that we've been discussing so far. And this derivative operator is called the Lie derivative. On tensors. And the point about this derivative operator is that it's with respect to this vector field V. If you don't have the vector field V, then you can't make sense of a Lie derivative. And how's it defined? Well, as all good derivatives, infinitesimally, the way it's defined is you think of the flow phi star as generating a kind of translation, and then that translation depends on a parameter t. So you translate a bit in the reverse direction, and then you subtract away the untranslated object. So in particular, we define the Lie derivative of a tensor field A1 through to K, B1 through to BL as the difference of two tensors. One tensor is located is the difference of two tensors they both arrive from a tensor field T, but this tensor here in yellow is evaluated at the point phi t of some point P, and this one in blue here is evaluated at P. So that way the tensor in yellow after phi star minus t acts on it is at the same point as the tensor in T in blue. So you can, I won't dwell too much on the mathematical details of the Lie derivative. You should, as a good exercise, check that LVT is a tensor field. So, and that you got to check that LV obeys the Leibniz property. And of course, that it's linear. Okay, all these properties are vital if you want to regard L as a kind of derivative operator. So there's a remark we can make at this stage before progressing and discussing more properties of the Lie derivative. It's defined also for scalar functions by following formula, namely that the Lie derivative applied to a scalar function is just the vector v applied to the scalar function at the point P. Now here's a homework. Argue that the Lie derivative v of a vector field component WA is none other than the commutator of v and w, the eighth component of the commutator of v and w. So it's a very important homework exercise. We're going to build on this when we discuss the action of the Lie derivative on more complicated tensor fields. So now we're going to derive an alternative formula. I've got a formula now for the Lie derivative, right? It's this thing with the blue and yellow tensors. But it's not so helpful if you want to talk about the action of L on composite tensor fields, or you want the specific action on a specific tensor field in terms of objects you can already compute. That's our goal now. So now note that for all dual vectors mu in the dual vector space Vp star, and all vectors Vp, so because of the action of the Lie derivative on scalar functions, we have that when you contract a dual vector against the normal vector, you get, well, that's a scalar function, right? So the Lie derivative of that, there's a formula for that. That's just applying v to this contraction. And we may as well give this thing a name, star. But there's also a second way to compute the action of a vector field on a scalar function, and that involves the covariant derivative associated to the metric that we have implicitly lying around here. So this is the second formula for the action of a vector on a scalar field is true not just for the one that we have for the metric under consideration, it's actually true for all covariant derivatives, which is kind of interesting, right? Now that's one way of computing the Lie derivative of this scalar contraction, but there's another way, right? And that's because Leibniz property allows us to compute the Lie derivative by separately applying the Lie derivative to the dual vector and to W. So I need to name this second equation here that we're going to make use of. Here we go. So the Leibniz property allows us to compute the Lie derivative first to the dual vector mu, then to the dual vector to the normal vector w. So we have that LV of mu a WA is none other than WA, and do L of V on mu A first, plus then do mu of A on L of V on W. But remember, star tells us that that's equal to the 8th component of the commutator of V and W. So we've combined two lines of derivation into one, and that actually determines the action of the Lie derivative on dual vectors explicitly. Firstly, apply the vector field V to the contraction of mu A and WA. Using the Leibniz property of the covariant derivative. So we've got two kinds of derivative operators here. And also note that the commutator of V and W, the 8th component, also has another expression in terms of covariant derivative operators that we derived. So we find noting these two formulae, we find that the action of the Lie derivative on a dual vector mu A is given by VB delta B on mu A plus mu B delta A on VB. So we have a lovely explicit formula now for the action of the Lie derivative on a dual vector. It involves the usual derivative operator delta. Now you can repeat this argument, do an induction, and argue by induction that for general tensor field T, the Lie derivative has the following form. So I'll leave that as an exercise. And this formula is true for all derivative operators delta. And now we're actually in a position to derive the gauge freedom of linearized general relativity. So the gauge freedom of general relativity is that of diffeomorphisms, but that of linearized general relativity will turn out to be, well, diffeomorphisms infinitesimally close to the identity. So let's actually derive that now. So if phi lambda is a one parameter group of diffeomorphisms, then, as I argued just before, M with the tensor field, the metric, and all the other tensor fields, and M with the metric phi lambda star applied to the metric, right? M is the same, right? We're applying a diffeomorphism from the manifold to itself. These two pairs represent the same spacetime. So if further we allow the metric G to depend smoothly on some parameter, we'll name this parameter also lambda, then we can ask what perturbations, and this is the key point, around the metric GAB 0, lambda equals 0, which just equals our original metric GAB, we can ask what kinds of perturbations of a metric look like local diffeomorphisms. So we're going to name these perturbations and call it gamma AB. So the perturbations of a general perturbation of a metric we'll call gamma AB, and you just get them by differentiating G with respect to lambda and then setting lambda equals 0. We're going to ask what perturbations of this form are of the form or are actually just infinitesimal diffeomorphisms. I.e. perturbations of the form gamma AB prime is of the form of d lambda, no longer of GAB lambda, not a general perturbation of the metric, but ones that are infinitesimal results of acting with our one parameter group of diffeomorphisms around lambda equals 0. So it's an exercise of just writing out the flow. We see that exactly gamma prime is exactly a perturbation arising from a diffeomorphism when gamma AB prime equals gamma AB minus LV times GAB, where V, right, there's a V mentioned here, and the V is the vector field generating phi. Oops, flow phi lambda. So there you go. We have now a definitive answer for what a perturbation generated by an infinitesimal diffeomorphism looks like, and hence these perturbations are precisely the gauge freedom of linearized general relativity. We have an answer, but we want a slightly more convenient formula for this. And we can get that by applying this formula that we derived earlier. Let's call it triple star maybe. We can actually get a slightly more explicit formula for the action of the derivative on the metric GAB. And we get V of C delta C GAB plus GCB delta A VC plus, of course, the action of the Lie derivative of the covariant derivative on the vector field itself. But if you note here, one of these terms will vanish, because if we use the metric, if we use the derivative operator determined by the metric, which we will, right, in general relativity, then the covariant derivative of the metric is 0, right? There's one of the key properties that defines the covariant derivative. So we're only left with two terms. And then we see that infinitesimal diffeomorphisms have this very particular form involving the covariant derivative applied to V. So now we can actually say what a gauge transformation explicitly of linearized general relativity looks like. It is then a transformation of the form where the gamma AB gets mapped to gamma AB prime, which is just equal to gamma AB, minus delta A VB minus delta B VA. And we can write that slightly more compactly using bracket notation there. This is a symmetrized application of the derivative operator. So if this vanishes, then we've got a particularly special form of infinitesimal gauge transformation. Namely, we have an infinitesimal isometry, right? We just mean that the metric doesn't change. And we have a name for such a thing. And that is VA is called a killing vector field. These will turn up in a handful of contexts in the future. And furthermore, this equation, which I've actually mentioned before, Killing's equation, is precisely this condition, that V generates an infinitesimal isometry. Now that we've got the precise linearized gauge degrees of freedom of linearized general relativity in hand, we're in a position to simplify the linearized Einstein equation and substantially simplify it to the point where we can pretty explicitly solve it without too much pain. So let's return now to our discussion of the linearized Einstein equation. And if you recall, the linearized Einstein equation, called I, has the form of GAB1, so the linearized Einstein tensor, which is DC gamma bar AB plus DC DB gamma A C bar minus a half A to B AB DC DD gamma CD bar, and that's all got to equal the stress energy tensor. And the aim now, I mean, this is a pretty complicated, I mean, it's linear, right? It's linear in gamma AB bar, so what are we complaining about? Well, nothing really. I mean, you could solve linear PDEs pretty easily, but you don't want to, right? You don't want to solve a complicated linear PDE when you can solve a simpler linear PDE. So that's just And we're in a position where we might be able to do this because we can use this linearized gauge freedom that we have to just find a new gauge, just do a diffeomorphism until this equation looks a bit simpler. So the aim of the game now is to find a linearized infinitesimal diffeomorphism which simplifies 1. You know, obviously there is one, right? I wouldn't go through all this trouble if there wasn't one. So what are we doing? We're looking for a vector field which generates an infinitesimal diffeomorphism. Let's call this vector field psi A, such that, what does this vector field got to do? Well, when we do this gauge transformation, when we rewrite the metric in terms of the new slightly perturbed but gauge equivalent metric, we want that the thingy that we get out, the new metric, we want that it simplifies equation 1. Okay, that would be pretty great if we could do that. And how do we do it? Well, there's a pretty simple condition. I mean, let's just go back to the equation and sort of guess what it might be. Kind of a helpful thing to do. You know, several places in this equation, you see the combination of a derivative operator applied to the metric, like here. So there's the derivative operator applied to the metric. Here the derivative operator is applied to the metric again. So maybe you could arrange for the first derivative of the metric to vanish. And you're going to see in a second how this equation actually helps us achieve this goal. So equation 2 then ensures that, and that combination actually vanishes. Okay, that's a little exercise. Just go through and substitute for gamma bar. Substitute this gauge transformed gamma AB into the expression for gamma bar AB, and then convince yourself that that's the case. So in this, now we've chosen a gauge, a simpler parameterization of the manifold, and many terms in the linearized Einstein's equation vanish now. And it becomes super simple now. So linearized Einstein's equation becomes dc gamma AB bar equals minus 16 pi TAB. It's almost as simple as it can be. This is like a four-dimensional version of Poisson's equation. And it's kind of interesting to note that this has includes, in the vacuum case where TAB equals 0, this is exactly the field equations for a spin 2 field. It's pretty interesting. Massless. And that's why people talk about the field equations of quantum gravity being for a spin 2 graviton field. All right, now we've got this linearized Einstein equation. We've massaged it into a form which is sufficiently simple that we might be able to really go ahead and solve it in some special cases. Well, now let's go ahead and solve it in some special cases. So we're going to take a look at one particular limit. This is really a vital limit if we're to have any faith in general relativity as being an extension of our known laws of physics applicable in the classical non-relativistic domain. Namely, we want to check out if general relativity is consistent with Newtonian gravity when gravity is weak and the relative motion of sources is much smaller than c. So this is Newtonian limit is the limit where or let's say A, gravity is weak. We don't want super strong gravitational fields. To talk about the Newtonian limit, we want relative motion of the sources being quite small. You don't want things zooming by at near the speed of light or orbiting each other with a orbital velocity that's close to the speed of light. And C, the material stresses have to be pretty small as well. You know, most of the mass energy density has to be in the form of mass energy density rather than material stress. So you can't have the material made up of little particles zooming around at the speed near the speed of light. Okay, these assumptions allow us to do some simplifications. They not only allow us to infer the existence of a global coordinate system. I mean, that's implicit or explicitly stated at the beginning of our discussion of linearized Einstein field equations. But they allow us to infer the existence of a global inertial coordinate system of the flat metric such that, you know, it's all very well to have a global inertial coordinate system, but furthermore such that the stress energy tensor has essentially just got the time component. So all the other 15 components are vanishing. So this TAB is the unit tangent vector pointing in the time direction. So that's an additional assumption. These assumptions allow us to make this additional simplification of the stress energy tensor. And what does it mean? Well, approximation 2 means that the momentum densities are small, and the stresses are small. And sources are slowly moving. Well, yeah. We've already assumed that, right? Since the source, however, what's a consequence of that assumption? Since the sources are slowly moving, what we're going to do is we're going to exploit that to look for solutions where the metric basically doesn't change. So that's what does that mean? That the time derivatives of gamma AB are neglected, right? So if the sources are sufficiently slowly moving, then we just assume that the gravitational field has instantaneously responded to the sources, and hence the time derivatives are vanishing. So a whole bunch of coordinates, components, sorry, of the linearized Einstein field equation will vanish. So here's the linearized Einstein's field equation in the gauge where everything is nice and simple. So gamma bar AB minus 16 pi TAB. So in this new coordinate system, a whole bunch of components will vanish. A whole bunch of components on the right hand side vanish. The only time the right hand side where the stress energy tensor appears is in the 0, 0 component. And in that case, we get minus 16 pi rho on the right hand side. Now this, I've drawn this delta squared here. Now this, I guess it's worth flagging this, right? This has got nothing to do with the covariant derivative. This is the usual Laplace operator. Your original three-dimensional Laplace operator. Because the time derivatives have vanished, the dc here simplifies to the Laplace operator, right? There's no fourth time component. So that's pretty convenient. So we're left with solving, well, a whole bunch of independent Poisson equations. Some with a source, one term with a source and 15 without. So the solution, let's just solve it, right? We know how to solve Poisson's equation. That's like, should be able to do it in your sleep by now. So the solution to Poisson's equation here, I don't know what we're going to call this equation. I'll just rewrite it rather than introduce yet another equation label. So the solution of this equation, well, under the assumption, right, that the metric vanishes, the metric perturbation vanishes as we go to infinity, well, that's pretty easy. There's not many solutions that have that property of of Laplace's equation. Namely, the metric components themselves have to vanish. It's pretty much the only way you can get it to work. And now we can use this information and further solve the final Poisson equation. Namely, we find that we can express the solution in the following terms. So t is this time-like unit vector pointing in the time, is the unit vector pointing in the time direction. And we've introduced this phi. What's phi? Well, phi is just, well, a solution to the Poisson equation. So we sort of fine. Okay, so we've got this solution now to the full linearized Einstein equations. So we're done, right? So this is, phi here is just the usual gravitational potential of Newton's theory. Well, let's see, are we done? I mean, like, okay, that's very good. We've solved Einstein's linearized Einstein equations in this particular limit, and we found something that looks suspiciously like Newtonian theory, but we haven't actually deduced that it's Newtonian, reduced to the Newtonian limit. To do that, we need to understand the motion of test particles. You know, how do test particles move in this particular geometry? Well, according to the fundamental assumption of general relativity, we have to solve the geodesic equation to get their motion, the motion of test particles. And the geodesic equation, well, that's, you know, an equation we've talked about several times now in this lecture course. In this particular context, we can write it out in terms of Christoffel symbols as follows. So that's the geodesic equation. And now that we've got the metric, we can work out gamma, and we can then thereby write out this differential equation and solve it and find the motion of test bodies. And this is with respect to global inertial coordinates. So, but we don't have to just tediously do all hundreds of calculations here. We can use a lot of simplifications to do this calculation quite quickly. And the first assumption we're going to make to simplify our lives is that of assuming that the test body moves slowly with respect to the speed of light, so that the derivative, the velocity of our test particle, is really 1, 0, 0, 0, right? That's the simplest assumption we can make about our test body, that it's moving, basically not moving at all, and that the coordinate time is equal to the proper time, or is approximately the same as the proper time. And when we make that assumption, we see that loads of equations here vanish, right? We don't have to, hardly any of the components here are going to matter for the calculation of the acceleration of our test particle. So the geodesic equation simplifies beautifully. And we only have to deal with these four components of the Christoffel symbols. And you can work out those components in terms of gamma. These four components here are just given by a minus a half d dx mu gamma naught naught. But that simplifies to d phi dx mu for the three components that are really important to us. So, you know, time derivatives are neglected here. And so the motion, we've now simplified things sufficiently to be able to express the motion of the test particle in terms of the gravitational potential or in terms of a quantity that we can now interpret as a gravitational potential, is minus grad phi. And this A vector is none other than the derivative of the position twice with respect to t. So the acceleration of the particle is defined with respect to the global inertial coordinate system. So we've managed to obtain exactly the acceleration of a test particle with respect to the gravitational field of a heavenly body in the Newtonian limit. However, it's worth stressing that the interpretation of the solution in general relativity is vastly different than in Newtonian theory. So, imagine we have a heavenly body like the sun. Well, in general relativity, it curves space-time via the mass energy density. The Earth, which is in our case the test body, is in free fall, and it moves on the geodesics of the curved space-time metric given by the sun, which is GAB, which solve Einstein's field equations. And because space-time is now curved, the geodesic motion of the test body actually closes and forms an orbit. And the final note is that the background inertial observers, which define the global inertial coordinate system, they're the ones in general relativity which are undergoing acceleration. That's in stark contrast to the Newtonian special relativity type picture that one has had previously. Okay, but that's it for this lecture today. Thank you very much, and goodbye.